Hello, everyone. Still wait a few minutes before I start to let people join the meeting. Okay, so I'll get started. All right. So the presentation is on how to use TypeScript effectively in backend applications. So before I dive in, I'll just briefly talk about me. So I currently work as a software engineer at MongoDB, so specifically on the documentation platform team. So anything documentation related, I kind of work on. So feel free to reach out to me if you have any questions or any suggestions you have about MongoDB documentation. Outside of that, I've had 5 years of full-time professional experience as a developer, and my name is again Brandon Lee. So, all right, so let's talk about the outline of this presentation. So, in the first section, we'll talk about TypeScript, what TypeScript is, and the benefits it provides. In the second section, we'll talk about common pitfalls of using TypeScript. And in the third section, we'll talk about how to make your TypeScript application more resilient and performant. And then finally, we'll just wrap up and summarize the presentation. All right, let's move on into the first section. So what is TypeScript and its benefits? So TypeScript is simply a superset of JavaScript. It allows developers to provide optional static type checking in their code. And specifically, this performs type checking at compile time. As I previously mentioned, it allows developers to provide type annotations, specifically to variables and functions and so forth. So let's move on to a quick demonstration of TypeScript and how it works. So let's move on to the sample that I've created. So here we have on line 1 a variable called string var, which is given the type annotation string. And how type annotations work in TypeScript, you provide the variable name followed by a colon and then the data type. So in this case, we provide the value hello, which is a string. So this is valid. TypeScript can also provide type definitions for object types using interfaces. And in this case, we have the interface called object interface, which has two properties, prop1, which is of type string, and then prop2, which is of type Boolean.
Hey, Brandon.
Yeah.
Sorry to interrupt. I don't think we can see what you're screen sharing.
Oh, sorry. Thank you so much. I appreciate that. Oopsies.
Do you mind if we could backtrack just a moment?
Yes, we can definitely backtrack. My apologies. All right, you can see this infinite window. So sorry about that. Again, it's my first time presenting, so apologies if there's any slip-ups. So hopefully that's the last one, but I'll restart. Okay, so how to use TypeScript applications effectively. I talked a bit about me, so you already know a little bit about me. I talked about the outline a bit, and then we're in the first section. And so we've talked briefly about what TypeScript is, and let's look at the demo now. So back to what I was discussing. So on line 1, we define a variable called string var, which is given the type annotation string. And this is defined by using colon followed by the variable name, followed by a colon, followed by the data type. And we assign the value hello, which is a string. We can also provide definitions or data types for objects using like an interface, for example. This interface has two properties, prop1, which is a string, and prop2, which is a Boolean. So as you can see.
Hi, Brandon. Sorry to interrupt you again. Would you? Oh, is that a slide?
Oh, sorry. Is it small?
Yes. Oh, yeah. This is better. Can you zoom in just a little more?
Of course. Yep. Thank you for pointing that out. Yep. Appreciate that.
Thank you.
Yep. Hopefully this is better. Okay. Cool. So anyways, so on line 8, we have the variable obj, which is provided the type annotation object interface. And as you can see, we have two properties. So two properties defined, object1 and object2. But as you can see on line 10, the property prop2 is given the value true, but as a string. And we get the following error message, type string is not assignable to type Boolean. So if you were to change this from the string true to the Boolean true, the error goes away. Also, if we add additional properties that do not exist in this interface definition, we'll receive an error. Also, we can provide type annotations to functions, as you can see here, for their parameters, as well as their return types. All right, so that's just that quick demonstration. Let's move on to the benefits of TypeScript. So as we saw from the previous demonstration, TypeScript allows us to catch errors before runtime. It enhances linting and error messaging, as we saw previously. And also, I believe it improves developer velocity when properly utilized. Also, I believe that TypeScript is excellent in self-documenting the code that you write. It takes a lot of the guesswork in what you can expect from functions or objects or various pieces of data throughout your application, as it provides the type annotation to tell you what you can expect, as opposed to using vanilla JavaScript, which does not provide that information. So let's look at another quick comparison of TypeScript versus JavaScript. So for this demonstration, we're going to look at calling a function in JavaScript versus calling a function in TypeScript. So in this file, index.js, we have a function called mystery function. And we'll see how, when using JavaScript, we don't get the same information that we get with TypeScript. So let's go ahead and just try calling the function with no arguments. Okay, so JavaScript, from our perspective, this looks valid from the perspective of JavaScript. And if we try running this code, we'll see if it actually executes successfully. So as we can see, we receive an error. It says we cannot read properties undefined prop1. So it appears that this mystery function takes an object that has a property called prop1. Okay, let's go ahead and try providing this property prop1. And it's a number, so I'll provide a number 32. Let's try running this again. So as we can see, we have a new result, but we run into another error. Specifically, we try calling the split method on the property prop2. So presumably, this prop2 property is a string because the split method is typically associated with strings. So let's go ahead and try adding that property. We assign the value hello, which is a string. Hopefully, this resolves the issue. As you can see, we get another error. We're missing another property, specifically prop3, which is an object that appears that has the property is mysterious. So as you can see right now, using the JavaScript approach, we don't have the useful information to know like what we need to call this, what we need to use, or what we need to provide to this function to make it execute successfully. So let's go ahead and look at this example using TypeScript. Clear out my log. All right, so let's call mystery function. And so right away, we get an error saying we are expecting one argument, but we have provided none. All right, and as you can see here, we get some information about the argument that we need to provide. It must satisfy this interface param object, which, if based off of this information, we can assume, right, that param object is going to be an object, so we'll give it just that. And as you can see, TypeScript gives us some additional information. Specifically, argument of type empty object is not assignable to the parameter of param object. And specifically, we're missing the following properties: prop1, prop2, and prop3. So let's go ahead and provide these properties to make sure we satisfy the argument for this function. So prop1, if we hover over it, it should be a number. Provide the value 35. Prop2 should be of type string. Let's go ahead and provide prop3, which again is going to be an object that has a single property, is mysterious, and this property is mysterious is a Boolean. Let's go ahead and provide that. Now let's go ahead and run this code. And as you can see, we actually are able to successfully run this without any errors. And also, too, we get So again, the big difference you can see right away is one, we get errors when we don't provide all of the properties that a function expects, and also we know which data type we can provide for that, or we need to provide for that property or parameter. And we also can see here too, there's another property that is optional, denoted by the question mark after it. So we can see immediately everything we need to provide, and it makes our developer experience much more smooth. So that was a quick demonstration just comparing TypeScript and JavaScript. So there are some drawback limitations of using TypeScript. I think, biggest drawback immediately with using TypeScript is the amount of upfront work required. So you're obviously going to have to put in the work to provide the type annotations, to get this type safety, and so forth. And that takes, obviously, it's not as simple as just writing code in JavaScript and running it as is. The second point, this is kind of like a personal, I think, drawback or limitation, which is TypeScript can lead to like a false sense of security if not properly typed. And we'll kind of talk about this more later, but a lot of times if you have code so TypeScript allows you to essentially turn off static type checking using the special type known as any. And if this is overly used or kind of not used cautiously, these data types or these variables or other pieces of the code that is not statically type checked may interact with code that is statically type checked. And this can lead to the statically type checked code running into errors because it expects the data to be a certain way, but it's not. And this is not like this is a drawback that it's less of a drawback, more of like something that's not necessarily intuitive right away. So a lot of times, so the last bullet point is TypeScript does not provide type safety at runtime, only compile time. And this is a key distinction. What this means is that when we run our code, we don't have that same type safety that we do when we're writing it. So when we write our code, we get information saying, okay, this is not a valid type, or this needs this property or this argument. But at runtime, that information is stripped away. So the actual data you get in the function, for example, that we just called, if we were to get the data from somewhere else, like maybe from like a file or an API call, it might not actually be what we expect it to be, like we expected it at compile time. And again, we'll go into more detail about what this means later on. So this is a nice segue into the common pitfalls of TypeScript. So we kind of talked a bit about that previously, and we'll kind of talk about the two big pitfalls, which is the usage of the type any, and also assuming that static type checking also includes runtime type checking. All right, let's briefly just talk about the any type. So as briefly mentioned before, the any type allows developers to forgo type checking for any specific variable. There are some benefits to using this type. Specifically, it's convenient when you have a large object that you don't want to type. Maybe you just need to access a single property, you know what it is. Or if you have a large object that you don't necessarily care about what the data types or what the data is, you maybe are just sending it off somewhere. Like, for example, you have a large object that you're writing to a file. For example, you don't necessarily care what the contents of it is. You just want it written to a file. But the big drawbacks are that it removes any benefits of static type checking. You don't get that nice linting or those type hints that we saw previously in the JavaScript versus TypeScript example. And this can also increase the frequency of type errors. So let's look at a quick demo, just kind of seeing like when any is used or how it like behaves when you do use it. So let's go look at that really quick. Okay. So in this example, we have a fairly large object. And say for this object, the only property we care about is company. Instead of defining an interface that defines all properties, we can simply just use, again, we provided the type annotation any here, so that we can then access this company property below, and then we can assign it here. But again, let's take a look at trying to access other properties of the object or the OBJ variable. And as you can see, we don't get any useful information. It's basically behaving like vanilla JavaScript. So it's a huge trade-off. And again, I don't recommend this approach, but we'll talk about other ways we can avoid this as well. In this other example here, we have this essentially a dummy function called send data somewhere. if we don't care about, again, what this accessing the properties of this data, we can assign the type annotation any and just basically use that as a way to kind of easily like move stuff around. But again, this is something that I generally would recommend avoid using. So we can go right into another demonstration, specifically talking about the second bullet point, which is the conflation of runtime type safety versus compile time type safety. So if we go to this file over here. So in this function, we're simply making an API request to this endpoint here. So from the perspective of TypeScript, everything looks valid, right? We have this interface employee get response, which has 3 properties: status, data, and message. The data property has for its type annotation an array of employee data objects, and that interface is defined right here. So we're using the library Axios to perform the RESTful API. We're basically creating a RESTful API, and specifically using a GET request to get data from this endpoint. And so what Axios allows you to do is provide what's called the generic type argument here, which essentially is telling this function that the data that you're going to get back should be of this type. And so as you can see here, in this example, we get the data object, which is going to be employee get response, which is the type we tell to give us back, essentially. And then for this part, or for this chunk of code right here, we're simply trying to get all of the employees' years employed, convert it to an array. And this is in our definition a number, but we're just, for the sake of the demonstration, to convert it to a string. And then we'll log the results. So let's go ahead and do that. Okay. But as you can see, we actually do run into an error. And as you can see, TypeScript doesn't give us an error, but when we run the code, we get this following error stating that cannot read properties of undefined reading to string. Specifically, employment length is not defined. Now, this goes against our expectation because, again, our interface defines this property for this object. But again, this data apparently that we're getting from the API does not actually return that information. So now that we talked about the pitfalls, let's talk about the ways we can make our application more resilient, and then also talk about how we can make it more performant. So one of the big ways, in my opinion, to improve the resiliency of your application is to provide runtime type checking. So even though TypeScript doesn't support runtime type checking, it does support it. So we can provide various checks at runtime to ensure we receive the data that we expect. And we can do this using specific functions called type guards. And these provide the runtime type checks. And the benefit, too, is that these also provide improved IntelliSense and linting as well. So it's not just purely from the benefit of runtime type safety, it also improves the developer experience. So let's talk a bit more about type guards. Type guards come in various different forms. Type guards can be built-in operators or checks. For example, we have type of, instance of, or in, and these can act as type guards. So type of is actually, and I believe instance of too is also, these are a part of JavaScript. They're not unique to TypeScript. But TypeScript can also use these two to, again, enhance the linting and IntelliSense, and again, provide that runtime type safety. The in operator specifically is also not a specific TypeScript operator. It's also used in JavaScript to check if properties exist within an object as a check. So we can use that as a type guard as well. And secondly, we can also define our own type guards by creating a function with a specific return signature. And so these user-defined type guards can either be a type predicate or an assertion. Type predicates return a Boolean, whereas the assertion will throw an error if the check fails. So now that we've talked a bit about what type guards are, let's go ahead and look at a quick demonstration of how they work. All right, so I have a bunch of code that I've written before, but we'll just walk through it. So in the first example, we talked about the type of operator can be used as a type guard. So in TypeScript, there's a specific data type or a specific type called unknown, which is similar to any, but it's a bit more type safe. So like the type any, unknown can be assigned any value. So you can get it can accept any kind of object or other kind of data type. It can be a string, Boolean, null, undefined, or again, any object, whatever. Any value can be assigned to it. The one key distinction between any and unknown is that no other value can be assigned, or unknown cannot be assigned to any other type except for any or unknown. So what that means is, for example, we have this variable called str unknown, string unknown, which is of type unknown. And if I were to assign this value or this variable to another variable called known string, which has a type annotation string, we'll receive an error. Type unknown is not assignable to type string. Also, unlike the type any, a variable that is given the type annotation unknown cannot have any methods or properties accessed. For example, we cannot do str unknown dot to string, or like in the previous example, we cannot call the trim method. But we can use the type of operator here. We can specifically check to see if the type of string unknown returns the value string. And if it does, we know that then TypeScript knows that this variable or this variable contains a string value. So as you can see here, we hover over the str unknown variable, and it is of type string. We also can call the .trim method. So like the type of operator, there's also the instance of operator. This is for comparing classes to ensure that the variable that you're looking at is an instance of that specific class. A common use case for this, in my experience, is when you're catching errors. For example, say you throw an error is thrown here and you catch it. By default, TypeScript will treat any errors as of type unknown. This is because you can technically throw anything. Like you can throw the number 21. This is also valid. So what you can do, since the error is an object, or error type is a class, we can call the instance of operator on E. And then in the context of this if statement, we can see that E has these properties of an error of an error object. And you can actually see here that E is of type error. So let's also move on to the last built-in type guard, which is using the in operator. So we have this function called print x or y. This function takes in a parameter called val, which can be of either type or another type. And these two types these two interfaces have different properties. The interface type has simply the property x, whereas the interface another type has the property y. So within the function, if you try accessing either property, you won't be able to by default if you don't check. So if I do val.y, this property just does not exist in this type. And if I do val.x, this property also does not exist. So as you can see here, if we say if x is in val, then we can log this and access this property x. And again, as you can see, we can see that the property or the parameter is of type. And then in the else statement, the same is true. We can access the property y, and the parameter val has a type annotation another type now in this context of this else if statement. Finally, if neither of these conditions are met, we reach the else statement where the type annotation for val is actually now never. This is essentially saying that this should not be a possible condition to meet. Like this type should not be possible given these two, or given this type annotation. So let's look in, now that we've discussed the built-in type guards, let's take a look at the ways we can define a type guard or a user-defined type guard. So again, there are two ways we can do that, using the type predicate or an assertion. Both are very similar, but have just very small distinctions or small differences between the two. So let's first take a look at the type predicate type guard. So to define a type guard, you simply create a function, and you provide the parameter you want to check, and then you simply have the following return type or return signature. Obj, the parameter name, is type. And this, what TypeScript then expects is for this function to return a Boolean. And so for this type guard, we're simply trying to ensure that obj is of type, which, if we recall, is an object or an interface that has a single property, x, which is of type number. With that in mind, we can construct our type guard. So the first thing we're checking is to see, is obj defined, or if it's not defined, or if it's not an object. If neither of these conditions are met, we want to return false. Next, once we get to this point, we know that the object, the obj parameter, is defined and it is an object. So we can do a cast here. So saying obj as type is essentially turning this into the type interface. So we can then grab the property x, and then we can finally return our final check. We're saying return type of x equals number. And as we recall, this is just making sure that this property x is actually type number, like we'd expect. So if we look down here, we can kind of see this in action. So we define a new object called unknown object, again, which is of type unknown. And this has a single property x, which is 32. If we call isType and provide this object, we can now access this property. And as you can see, it's now of type. But if we go outside of this if statement and try accessing this property, we're not able to. Now, looking at the assertion is essentially the same thing as using the type predicate for the type guard. But the one difference is, instead of returning a value, you simply throw an error if the condition is not met for your type guard. So the logic is just the same. The checks are the same. But when the check fails, we simply throw. And the difference in behavior is that we call assert isType, and then we can access the property of unknown obj because we know it will be type. This is because we now throw an error. So if an error is thrown, we're not going to be able to get to this point in the code. So that's how the assert type guard works. All right. So now that we've talked about type guards, let's talk about when we'd want to use this kind of type checking, specifically the runtime type checking. In my opinion, it's just a judgment call. So it's based on a few factors. The first factor is of when we want to use this is when the data is coming from outside the application. Like if you're getting data from a database, or you're receiving data from an API, you're receiving an API request. Maybe your backend application is a REST API. You might want to consider having this runtime type checking. Another important factor to consider is how much control you have over this incoming data. For example, if you have little to no incoming control with the incoming request, for example, you might want to provide runtime type safety through type checking. This is because you aren't necessarily confident that the data will correspond exactly with your code base. And so with that said, this is why I believe it to be a judgment call, because if you're confident, it's like, say, for example, the requests are coming from an application that you write and you control, well, you have higher confidence knowing that the data that will be sent to the other application is going to be accurate and will conform to the types that you've defined. So you might not necessarily need type checking, even though the data is coming outside of that specific API. So now that we talked about runtime type safety and type guards, let's kind of go back to that one demo where we're making an Axios request, but now using this runtime type safety. Oh, sorry. Gotta go to the demo. Okay. So as you can see, there's a bit more going on here. There's a bit more code, but it is essentially doing the same thing. So we have the same function as before, the main function, which is making an Axios it's making a GET request to the same endpoint. But now we have a type guard here. And so what this type guard is doing is essentially checking the object to make sure it's defined. And then we loop through all of the employee data objects to make sure that we have no objects, employee data objects that are not valid. So we want to make sure that every employee data object is what we expect it to look like, which is to have all of these properties. With that said, now that we are, and another key distinction here from the previous example is that this is kind of like a personal preference. You don't have to do it this way. But I like to make sure that I do this. This essentially forces me to do the checking. I say that the data type, instead of providing the exact data type, the employee get response, the employee get response as the generic type argument, I provide unknown because then I have to check. Otherwise, I can't access any properties of the data object. So what I do here is we check if the employee, make sure this response data is going to be an employee get response. And if we don't, we log this information out and then we return. But from here on out, the rest of the code, we can expect that the data will be an employee get response because we return if it is not. So now let's take a quick look and see what the behavior is now that we've changed our code a little bit to use runtime type safety. As you can see here now, the data is not valid, but we have a much more easily readable error message. So this example is pretty contrived. It might not necessarily portray all the benefits. It might not seem necessary to do this. And if your code is this simple, you probably don't need all of this type checking. But if your application grows, and say, for example, the data you get back from this API call gets used in various different parts of your code base, and maybe you have properties that don't get accessed until much further along the line in your code base, you might not get these undefined errors until much later on. And this leads to very confusing undefined errors because maybe in your code later on, you expect it to exist because you don't check here, but you still assign that data type anyways. So as you make various function calls throughout your code base and this data gets passed around, things that are supposed to exist won't actually exist when you expect them to. So this is why I believe it to be useful. So now let's move on to how we can improve TypeScript performance. So performance in this context refers to compiling and linting performance. As applications grow, compilation and linting time increases. If you've ever worked in a large TypeScript code base, it can be very slow when trying to make changes or view like the type hinting or type linting in your editor, specifically like using VS Code. And this obviously impacts developer productivity. So let's talk about one way we can improve performance. Specifically, if you can, prefer interfaces over type aliases, and specifically prefer the interfaces when combining types, as interfaces are more efficient at combining types than type aliases. Interfaces, when they're combined with the extends keyword, create a single flat object, and this allows you to detect duplicate properties, which helps resolve like mismatched types for the same property. When using a type alias, properties are recursively merged, and this can lead to the combined types having the type never, which is not a great situation to be in. Let's look at a quick demonstration of this in real. In this brief demonstration, we have two interfaces, interface A and interface B. Interface B extends interface A, but the interface B defines the property Z here and gives it the type annotation string, whereas the type Z or the property Z defined in the interface A is assigned type Boolean. And as you can see here, we get this error message stating that interface B incorrectly extends interface E and that these properties are incompatible. So on line 11, we define the type alias X, which is essentially the same. These are essentially the same way to define an object, but this is using a type alias. And we can combine this type alias X with this type definition, object definition here, like so. So these are identical in combining object definitions or object types. But as you can see here, we don't get an error. And also, if you look at the type y equals never. And again, this doesn't give us any information as to how we can resolve it. So again, if you can, prefer using interfaces over types. All right. Another way to improve performance is to prefer base types over unions. So when using unions of object types, TypeScript needs to perform an element-wise check on each property. So if possible, create a base type that can be extended, like in the example below. So the example that I guess the approach you want to avoid is going to be from lines 10 to 21. So as you can see on line 21, we define a function called process job with union. It takes in a single parameter with a type of simple job, the union type simple job combined with simple compute job. So what this happens whenever you call this function, what will happen is TypeScript will have to compare all of the properties within that object with both of these interfaces. And if you get very, very large objects, this can be quite cumbersome and slow down the IntelliSense quite a bit. Also, always provide type annotations, as type annotations reduce the amount of work the compiler needs to do. Also, if possible, when making for example, a return type, when defining the return type, using name types are preferred as they are more compact than what the compiler would infer. So I have a little example here. The return object function on the left has a kind of messy, large return type, whereas if we define that return type as an interface, we get a much more compact representation of that object type. All right, so that's kind of wraps up this presentation. I know it was a lot of information all at once, so apologies if I couldn't go into as much depth on a certain topic, but if you want more information, here are some really great resources that I used personally, or that I found very useful, and obviously I'll share the links to each of these as well after the presentation. So let's go ahead and move on to the Q&A. All right. All right, and if you have any questions, again, feel free to leave that in the Q&A section, and I'll give people a few minutes to go ahead and leave any questions if they have any. Okay, I got a question from Yusuf. This is a good question. Do type checks slow down performance? They do to a degree, because you're doing additional work by checking. Obviously, you're doing additional operations at runtime. So yes, it does cause a runtime performance hit. But I think depending on how much checking you're doing, it should be relatively negligible. But obviously, that is something that will depend on the specific checks you're doing. And this is another, I guess, like trade-off you'd have to consider or factor in is the performance hit or penalty that you confer from doing this check, is that actually worth the safety you get at the end of the day? So, okay, another question from Divya. Are there any tools to convert JavaScript to TypeScript for an existing code base? Or does it have to be a rewrite? Specifically, she's asking for a React application. There are not any tools I know of off the top of my head, unfortunately. So I'm sorry, I won't be able to answer that question directly. I think what you can do too, what you could look into as like a kind of intermediary step between going from JavaScript to TypeScript, is create declaration files. So declaration files are a way to kind of say that, okay, I have JavaScript code, but here's like, if you were to use TypeScript, here are some data types, like maybe I have interfaces or function call signatures for my JavaScript code. So when you use it in TypeScript, you can see that. Okay, I got another question from Chase. This is a good question. His question is, did I catch correctly that the type declaration isn't as efficient as an interface when it comes to extending them? Yes, that's correct. I guess that's more not necessarily a performance issue, more of like it's a developer experience kind of penalty, I guess you pay by using a type alias as opposed to an interface when defining object types, specifically combining them. Because like as in the demonstration, you don't get the same. Well, I guess the recursive merging process, I believe it confers a performance penalty during the compilation of your TypeScript code. So there might be a slight performance benefit there. And also, again, to the way it kind of handles those conflicts is not very useful for the developer. It makes it quite confusing and opaque trying to resolve that. So again, great question. All right. Anything else? All right. Well, I think I'll wrap it up. And I just want to say thank you, everyone, for taking the time out of your day to listen to this presentation. Hopefully you found something useful, and I'll make sure to provide any additional information that you need. Oh, actually, sorry, I got one more message. Oh, just, yeah, thank you. I'm glad to hear, Chase. Yeah, Amy, Divya, Yusuf, really appreciate you all joining. So thank you so much. Hope you have a great day. All right. Take care, everyone.